Okay, so today we're going to talk about what types of energy there are. We're going to be focusing on what is energy, what different types there are, and what does it mean that there are different types of energy. So let's start with the physics definition. What is energy? All right, well, energy, the physics definition, is simply the ability to do work. Think about it. Can you do work if you don't have energy? No. Units of energy are joules. That's joules with a J, capital J. And notice something that what else has units of joules? Energy and work have the same. They're both joules. Thus, you can see how work and energy are tied together intimately. Okay, so what is kinetic energy? This is our first type of energy. So type 1. We're going to look at kinetic energy. Kinetic means moving. So this is energy possessed due to motion. Okay? Kinetic energy is a big K, and the formula for that is 1/2 mv squared. And you can see, so that kinetic energy has to do with mass and velocity. Okay, so either something has a large mass, to have a big kinetic energy, has a large mass with a low velocity or a high velocity, doesn't matter. Large mass is going to give you high kinetic energy. Think about it. It takes a lot of energy to get it moving and keep it moving. Okay, it's moving. If you take a really heavy object and get it moving, it's going to take a lot to stop it. That's energy. Or to have a high kinetic energy, you can have a low mass, a small mass, but it has to have a really high velocity. But you think about that too. Think about something with an extremely low mass. That would be like an electron. Electron is orbiting around the nucleus of an atom. It's orbiting very quickly. Okay, so it's moving very quickly, and it would take a lot of energy to move it out of that orbit. That is energy. So if you want to think about it, is that relationship for high kinetic energy is either high mass or high velocity, or both. If you have a high mass and a high velocity, that's really, really, really got a lot of kinetic energy. So how do we solve for kinetic energy and apply the work energy theorem? Okay, oh, it says work energy. This should say work energy theorem. Okay, work is done when what? A force, in other words, how do we get something moving? A force acts over a distance. Okay, we know this. All right, when we push something over a distance, we are doing work. We can feel it. And this is going to change the energy of a system. If we shove something across the floor, we're going from a low energy state to a high energy state because we're putting work into it. Makes sense if you think about it. So what is the work energy theorem? It says that if we transfer work from one object to another, or from one form to another, so it's from one object to another, or from one form to another, right? The work energy theorem comes from Newton's second law. Okay, what does that mean? Well, the first thing we're going to talk about is this. If we do work on a system, what are we doing? In other words, what's going to happen to the energy? If I shove that block, I'm doing work on that block. Is the energy going to go up or down? It really is common sense here. So doing work on a system, you are correct. This is positive work. is going to increase. I hope you thought that. Increase the energy. Okay? Now, if you do work on a system which is negative work, in other words, what would the difference between negative work be and positive work be? If it's negative work, when you think about it, something sliding across the room and we want to slow it down. We push back against it, or it experiences something like friction, okay? So positive work would be an applied force in the same direction of the motion, and negative work would be an applied force in the opposite direction of the motion, okay? So negative work is going to decrease the energy of the system, okay? Either way, we're increasing or decreasing the work, right? Which means that we have a net work which is going to be equal to the change in energy. And since the energy has to do right now with motion, it's going to be equal to the change in kinetic energy. And this is our work energy theorem. In other words, work, W equals delta K, change in kinetic energy. Now, when we do work on a system, it increases, and if we do work if the system does work, it loses energy. So work on the system decreases or loses energy. Think about it in terms of friction. It's having to, think about this, the system is having to expend energy somehow. It's hitting this rough patch, and it's slowing down, it's losing energy. Well, what is it expending energy on? Generating heat from the frictional surfaces touching each other. That's really what we're looking at here, okay? So, let's look at an example. We have a 15 kilogram mass. Speed changes from 10 meters a second to 30 meters per second in 8 seconds by a constant force. How much energy does it gain? And what's the magnitude of the constant force? So let's start with A. Energy does the object gain? Work, which is energy gained, is going to be the change in kinetic energy. So we need to figure out that is going to be 1/2 mv final squared minus 1/2 mv initial squared. Okay, well, we can take the 1/2 m out. So v final squared minus the initial squared. So we're just going to plug in now. 1/2 the mass, which is 15, times the final was 30. Square that, minus 10 squared. Notice that we square before we subtract. And what we end up with is 6,000. And that would be in joules, okay? So the change in kinetic energy is 6,000 joules. So it gains 6,000 joules of energy, all right? It's positive. Notice that if it were losing speed, that would be negative. And so you would know it was a loss of energy. The sign will tell you whether it's a gain or a loss. All right, now part B asks us the force. What is the force magnitude of the constant force? Well, we know work is also tied to force. It is force over distance, so FD. So force, if we manipulate this equation, force is going to be equal to, divide both sides by D, we get work divided by distance. Well, we know the work, it's 6,000 joules. We know the distance. Do we know the distance? Uh-oh, we don't know the distance. So guess what we have to go find? We have to go use kinematics. find this. We know V initial, we know V final, we know the time. So the distance, in other words, delta x, if we think about it as starting at 0, is going to be equal to V initial t plus 1/2, what? AT squared. We don't have A, so we can't use this one, so we're going to have to use, if we only know the initial and final and the time, we're going to have to use the one we don't use very much, which is V initial plus V final times the time divided by 2. In other words, the average velocity times the time. So let's find this. We know V initial is 10 plus 30 is V final. Multiply that by the time, which was for 8 seconds, and divide that all by 2. And we get 160 meters. Okay, so we can plug that in over here. 160. Take that and divide, and you get 37.5 newtons. Okay? 37.5 newtons of force. All right, so example B. We got a textbook sliding across the floor. All right, textbook sliding across the floor, initially traveling at 6 meters per second. We've got coefficient of sliding friction between the book and the floor is 0.15. So, first thing you ask yourself, it says find the distance required for the book to stop. Is this thing gaining or losing energy? I hope you think losing, because it's going to be going slower at the end, isn't it? Okay, so what is the first thing we know? First thing we should know is friction does negative work, doesn't it? Okay, so what do we know here? Work due to friction is going to be equal to the change in kinetic energy. All right, well, what is the work due to friction? Work due to friction, change in kinetic energy is going to be, well, that's going to be 1/2 the mass, if you remember, and we said it was V final squared minus V initial squared. Well, we know V initial, we also know V final. V initial is 6 meters per second, and V final is what? Comes to a stop, so 0 meters per second. So if we figure this out, we have 1/2 the mass. Let's just leave that for now. V final is going to be 0 minus 6 squared. So what we have here is what? 18. This is 36, negative 36. Half of that is negative 18 times the mass. We don't know what the mass is yet, so now let's figure that out. What would the work due to friction be? Work due to friction would be the force due to friction times the distance. Okay, well, force due to friction is mu times the normal force times distance. Well, normal force, if it's sitting on a book, if we do a free body diagram, we have normal force going up. And what do we have going down? mg. Okay, so this is going to be equal to mu times mg times the distance. And that is going to be equal to that delta K. Well, what is that delta K? Well, we know what mu is. It's 0.15. We don't know m. We know g is 10. Here's d equals delta K, which is negative 18m. Okay? Well, this is negative, isn't it? So we've got negative. We've got m's going away, so yay on that. And to find the d, the distance it travels, we simply have to take that negative 18 and divide it by negative 0.15 times 10. What do we end up with? 12. And that would be meters as its distance. So you can see what we're doing. We're taking this definition of work, and then we're taking delta K, and we're setting them equal and solving. All right, so let's look at this one. We have a graph. We've got a force distance graph. You know what that means? Force distance, what do we know about work? We said work was equal to force times distance, didn't we? So to find the work on this graph, what's it going to be? It's going to be the area, isn't it? Under the curve. Okay, so what is the area under the curve? It says, what's the speed of the object? Well, if we want to find the speed of the object, what do we know about work? Work is equal to change in kinetic energy. So we're going to take this area and set it equal to the change in kinetic energy. Okay, so at 5, that means we're trying to find this entire area right here. Well, that is 1/2 base times height, right? And that's going to be equal to 1/2 the mass times v final squared minus v initial squared. Okay, this is initially at rest, so this is 0. The halves go away. The base is 5. The height of this guy is 8. The mass is 0.4. And then we have velocity final squared. Now all we have to do is work this out, do the math, and we get v final is equal to 10 meters per second. Okay, divide by 0.4 and take the square root, right? So we divide by 0.4, divide by 0.4, that goes away, and we take the square root. All right, so now, second type of energy. Potential energy. Something has potential to move. What do we mean by having potential to move? That means it is energy that's stored, that it's due to its position. Think about it. If you hold something up above the ground, you're holding it above the ground, pencil, whatever, it has the potential to move if you let go of it. Well, it's the higher you hold it, the more potential it has to move, because it's going to fall further. It's going to do more work. Okay, so there's a direct relationship between that gravitational potential energy, amongst other things. Springs have potential energy. If we squish a spring down and we move our hand, it now has the potential to move, because if I move my hand, what's going to happen? It's going to spring out, isn't it? Or if I pull it down, it's going to spring back up. So that also has potential to move, which means it has potential energy. All right, and it's positional, okay? So, unpotential energy, we have gravitational potential energy, which means that it's due to its height above some reference position, okay? Remember what we said, if we hold it up, it can fall, all right? Now, think about it. The amount of potential energy an object has is equal to the work done given that object that energy. And it says usually through moving to a location. So what is the formula for gravitational potential energy? All right, well, if you think about it, if we have something right here, some mass m, and we've got some reference point down here, really what we're measuring is what's going to happen with gravity and what through some distance falling. So this is going to really make sense. The things that are going to give the potential energy is how much mass it has, gravity, which doesn't change, the acceleration of the object, and then how far it's falling. So we use U for potential energy. We're going to use U sub G for gravitational potential energy, and it's going to be directly product of mg, which is the force, right? This is the force due to gravity, times the distance it falls, which is h. So mgh is going to be our formula. Where did that come from? F times d. All right, mgh equal to the work done to bring the object to that height. All right, so let's look at this. A car drives up a friction. Now this is going to make problem solving much easier, guys, because now we don't care about what's happening in between, and we don't have to worry about Newton's law so much anymore. We're simply looking at the energy state at the beginning and the energy state at the end. Okay, so now let's look at example D. An 800 kilogram car drives up a frictionless surface with constant speed. It reaches a point 20 meters above its starting point. All right. What's the gravitational potential energy of the car at the top? Well, let's look at it. Gravitational potential energy in part A is going to be equal to mgh at the end? Well, the mass of the car is 800. Gravity, of course, is 10. And at h, it is 20 meters up. So if we multiply those together, we get 160,000 joules of energy. That's how much potential it has. Then it says B, what's the work required to drive the car up the incline? Well, here's a couple of things. We noticed it was at a constant speed and it's frictionless. So if there's no friction, are we losing any energy? Not according to this problem. No friction equals no energy lost. So the work is going to be equal to the gravitational potential energy, or the change in gravitational potential energy. Maybe we should better say that, because it's that change in energy. And I want you to think about it. You saw in the little exercise that we looked at in class when we did the skate park activity that think about why this has changed, that as kinetic energy went up, potential energy went down the same amount if we didn't have any friction involved, didn't it? So there's this opposite relationship between the two. Okay, so we have the change in potential energy here. So we are going to lose the amount of potential energy it has, causing it to go up the hill. Okay? So work is going to be equal to the change in potential energy. So work is going to be 160,000 joules. Is going to be done. To move the car up the hill. Okay? Did I finish this one? I did. All right. All right, so now let's look at Hooke's law. What do we know about Hooke's law? Hooke's law is going to tell us about elastic potential energy. We usually call this spring U sub S, or U sub E if you want to think of it as elastic potential energy. So what does Hooke's law say? When we have a spring that is some distance from equilibrium, in other words, this is equilibrium. This first one is equilibrium right here. This is at rest. Now we have stretched it to some point out here. We've stretched it. This distance that we stretched it represents, or we could call it K, because usually with the spring we call the distance X. We'll call this some distance X, okay? Then based on how stiff the spring is, that's going to tell us how much work is done. So Hooke's law actually relates the distance the spring is stretched and this is measured from equilibrium, and that is its resting unstretched position. To the force needed to stretch or compress the spring. Now that's directly related to the stiffness of the spring. The stiffer the spring is, the more force it's going to require, isn't it? So this is going to make sense. F is going to be equal to negative kx. This is what we call our spring constant. Bigger it is, the stiffer the spring. Spring constant is in newtons per meter, okay? And x is going to be the distance stretched from equilibrium or compressed. Okay? So now, you can see as K goes up, the force goes up, doesn't it? So stiffer springs mean more force required, and because stiffer springs have higher spring constants. Okay? Now, why is there a negative in front? Why is this negative there? Read what this says. The negative sign in front of K indicates the force is the opposite direction of the displacement. What do you think about what that means? Stretch out a spring. If you take a string and you stretch it out and you let go, you stretched it, say you stretched it to the right. What direction when you let go is it going to go? It's going to move to the left. So the force actually wants it to move in the opposite direction of what it took to stretch it to that or compress it to that length, x. It's going to go in the opposite direction. Now, Hooke's law applies to anything that is elastic, not just springs. It works with rubber bands. It works with anything that's plastic that stretches, or anything that's not plastic that stretches. We actually technically could stretch just about anything, right? Anything we can stretch, we can treat it as a spring in physics, all right? So now, work to stretch a spring. We still have a force, an x. So I want you to think about that. Where is the work? The work is still going to be what? Work is FD, right? So it's still going to be area under the curve. Well, let's see what that is. With F, it's going to be area, that's a triangle, so 1/2 the base, which is x, times the force, which is the height, right? 1/2 base times height. Well, we know what that F is, though. 1/2 x times kx, right? So this is going to be 1/2 kx squared. And that is the work done to stretch a spring. Looks familiar, doesn't it? Work for and I want you to think about why it's positive and not negative. It's the change, isn't it? Well, if it's negative, then the change is going to end up being the difference between a negative times a negative is a positive, okay? So, but this also looks a little bit like 1/2 mv squared, doesn't it? Sure does. So for springs, 1/2 mv squared becomes 1/2 kx squared. So this is work due to stretching a spring, or work elastic. So, U elastic is going to be the work done to stretch the spring, which is going to be 1/2 kx squared. Let's look at an example. Spring is stretched by 10 meters by a force of 75 newtons. Okay, no problem. What's the spring constant of the spring? Oh, okay, well, let's figure it out. We know that force is equal to what? Negative kx, right? Well, that force is stretched That's going to be 75, correct? But it's the force is in the opposite direction of the motion, minus K times stretch 10 meters. So what we get is a K that is 75 divided by 10, which is what? 7.5. Force is newtons divided by distance, which is meters. So there's that newtons per meter that we have. B, K is always going to be positive, by the way. So even if you forget that sign, you could leave the sign off, the negative sign off, because you know the force is in the opposite direction of the motion. So if K is positive 10, then F has to be negative 75. All right. Now, what happens if the spring is placed vertically and a 3-kilogram watermelon is hung from the spring? Calculate the elastic potential energy stored in the spring at this point. So the first thing we need to figure out is how far is it going to stretch? Well, let's think about that. If we do a little free body diagram, what's happening? We've got mg going down, and then we've got it resisting that, the force of the spring. The elastic force is resisting that. So that's what our free body diagram looks like. So if we look at the spring force, which is Kx, that's going to be equal and opposite to, well, would be negative Kx, equal and opposite to negative mg. Well, the negatives go away, so Kx is really equal and opposite mg. So we know what K is, we know what X, we don't know what X is, we're looking for that. So what we're going to find is X is equal to mg divided by K. Well, what is that? The mass was, what, 3? Gravity's 10, and we're dividing it by 7.5. So what we get is a stretch of 4 meters. Now we can actually figure out what it is. So now we can actually figure out that U elastic or U spring is going to be equal to 1/2 Kx squared. So this is going to be 1/2 K, which was 7.5, times that 4 squared. Well, that ends up being 135, and this would be joules. So it's going to take 135 joules of energy to stretch the spring down that far, thus meaning it contains 135 joules of energy to change into something else like motion if you let go, if you take the watermelon off. Okay? All right. So, some things about work and energy that you need to know, and I want you to just listen to this. There are misconceptions that people have with energy. First thing is that energy is a product of an activity. Not necessarily true. Energy transferred is a product of energy, but we don't create energy. All the energy that's around is there already. It's just in a different form. Thus, that switching between types of energy that you saw in the skate park activity that we did, all right? Back and forth energy is moving back and forth into different types, from kinetic to potential to frictional energy to, you see what I'm saying, to heat energy, to sound. All of those things are types of energy, all right? And so it can change form, but we can't ever create any new or get rid of any, simply changing form. Energy is associated only with movement. What we saw today, that's not the case. Energy is associated with movement, but there is potential energy, okay? Energy is a force. Energy is not a force. Energy is the product of a force over a distance, okay? And energy is only found in living objects. That's a biggie. Well, that's not true. We've been talking about cars and springs and blocks and pencils and stuff, and those are clearly not living objects. Every object has the ability to have energy and convert one type of energy to another. Now, we just do it naturally through eating. That's how we actually get our energy. Is we eat and we convert our energy to another form in our body, which fuels our cells, which then fuels us, our ability to move. and that's kind of a unique thing to living things, is our ability to change chemically energy into activity, motion. All right? And that energy, last one, energy is a substance. Energy is not a substance. Okay? It's a state. It is not matter. It is simply a state. The things that we get out of energy are simply from they're the same structure, but they appear different. Okay? So, like, say, water, an ice cube versus liquid water versus steam. All of those states change because energy is put into a system. You have to put energy into a system to heat up that ice cube to cause it to melt and become water. And then you have to add more heat, and then it boils and becomes a gas or steam. Okay? So you can change the state of them, but they actually have, water, steam, and ice have the same molecular structure. It's still H2O. Okay? 2 hydrogens and an oxygen molecule connected together. It's how they move that causes them to be less movement, less energy, colder and ice, more movement, more energy, liquid, rapid movement, moving all over the place, steam, and a gas. All right, that's it for today.